In this video, we're going to take a quick look at integrals that result in inverse trig functions. And mostly we're going to kind of use these as formulas for us to find integrals. But the thing to remember is that where all of these come from and what's kind of going on behind the scenes here is that they are the antiderivative of our inverse trig functions. So, remembering that the derivative of inverse sine of x is 1 over the square root of 1 minus x squared. That's, a little bit how we get to, again, if we here let a equal 1, kind of think about that, then we would get that the integral of 1 over the square root of a squared minus u squared, and a is a constant, then that's the inverse sine of u over the absolute value of a. So what the formulas are in the book is they're a little bit more, what's the word I'm looking for here? General, that's the word, than sort of the really specific formula that we have here, if we just go straight from what the derivative is and take the antiderivative. So this formula that we've got here in our definition is just a little bit more general, and it says, we don't have to necessarily just have 1 minus x squared. We could have 9 minus x squared, or any number that we could write, even if it was, for example, the square root of 5 minus x squared, we could rewrite that as the square root of 5, the square root of 5 being squared minus x squared. So we could take that a or whatever constant sitting there and write it as something being squared. So kind of keep that in mind as we go on further with this. But again, we have a similar formula for 1 over a squared plus u squared. And again, that's coming from that the derivative of inverse tangent is 1 over 1 plus x squared. And the last one, which we use, say probably a little bit less than the other two, is the antiderivative, where it results in inverse secant. And the derivative of inverse secant is 1 over the absolute value of x times the square root of x squared minus 1. Yeah, I hope I said that right. Lost track of what I was saying there, but I wrote it right. So that's where these are all coming from. If you want to see, how really specifically they get to these sort of more general formula where they replace the 1 that we have here in these sort of really specific formulas with any number that's being squared, then you can take a look in the textbook. They prove the first one, the inverse sine formula, with implicit differentiation. So you can take a look at how they prove that. All right, so let's do a couple quick examples. And again, this is really just us using the formula, recognizing which one we have, which one of these sort of 3 formulas we have, and maybe rewriting it a little bit just so we can see exactly what we've got. So this is an example of the first, sorry about that, this first formula right here, because we've got the square root of our 2 things being subtracted and the x is after the subtraction, which is what we've got up here in our formula. So I'm going to rewrite this just a little bit, and we're going to get the integral of 1 over 5 squared minus 3x being squared. So what I'm trying to do is to rewrite this to look like it's a squared minus u squared. So a perfect square minus a perfect square, because then it's more in the format that we have up above. And we do have to do substitution with this because we don't have just plain old x that's being squared. So here we're going to need to let u be that 3x. So it's not the whole thing. It's not that whole 3x being squared. It's not the 9x squared. It's just what's inside of that. And we'll see here why in a second. And then so the derivative of that du dx is 3. And so solving and getting everything together, we're going to get 1/3 du is equal to dx. So that's going to make our integral equal to 1/3 1 over the square root of 5 squared minus u squared du. So we still want that u squared sitting there, so we don't want to use that squared as part of our substitution. So that squared stays there, and it's just what's inside of that being squared. Because again, we're trying to get it to look as much as we can like what we have that up there with that a squared minus u squared. So in the case of the situation that we have here in this specific problem, we've got right here, a is equal to 5. So when we go back up and look at our formula, our answer is going to be inverse sine of u over the absolute value of a. So that's going to give us 1/3 times the inverse sine of u over the absolute value of a, which is 5, and then plus our constant. So now making this look nice and getting this back in terms of x, because u is 3x, and the absolute value of 5 is 5. So we can write it like that, and then plus RC. So that's all we have to do. So it's a little bit of rewriting just so we can realize, how it exactly fits with that formula. But once we kind of get it written how it's supposed to look in the formula, it's not too bad. Let's take a look at one more of these just so we can get the idea. So here we've got 1 over 49 plus 4x squared. So again, it's a matter of us kind of going back up here and looking at our 3 different options that we have and saying, okay, what kind of thing is it that we have? Well, this one doesn't have a square root, and it's got a plus, so that's telling me that we've got the situation here in formula number 2. So what I want to do is try to rewrite our integral as much as possible to get this to look like the integral of 1 over a squared plus u squared du. So the first thing I'm going to do is rewrite the terms on the bottom as perfect squares. Oops, already that's going to be 2x, that's going to be squared. So in this case, our a is 7, and this 2x, that's going to be our u. And that's also nice because that really sets up the substitution for us so that we can go that du dx is equal to 2x, and then just like up above, we get 1/2 du is equal to, it's not an x there, it's just a 2, is equal to dx. There we go. So then this makes our integral, the integral of 1/2 times 1 over 7 squared plus now u squared, and oops, boy, I'm having real issues with my variables today, so don't worry if you do that sometimes. I do it all the time. So now it looks pretty much exactly like we have our formula here. We've got a there is 7 and our u that's being squared, and so our integral is going to be 1/2. Maybe I need to go back up and look at the formula, make sure we got them all. So this one's got a constant that we add out in the front, so it adds a 1 over a, and then inverse tangent of u divided by a. So this 1/2, remember that's coming from in our integral, but then 1 over u, or 1 over a, excuse me, and then inverse tangent of u over a plus c. So again, this is just from us doing that formula that's written up above, and then simplifying things a little bit and getting everything back in terms of x. We get 1/14 inverse tangent of 2x over 7 plus c.